Well, thank you very much, Province Councillor Stefan Keinertei and Dalibor Straski, the anti-nuclear power officer. Well, Stefan, you have already provided a brief overview of what we are going to focus on today, focus in detail on today. We will try to make sure that this fairy tale will not become a reality, and we will base our findings on scientific facts. And right at the beginning, I would like to announce a change. Matthias Englert, our first expert, will provide an overview of the SMRs, the small modular reactors, and for case of emergency in his family, he could not tell whether he would be able to come to Austria today. And then it was announced that there will be a strike of the Federal Railways in Germany, and we asked him to record his presentation because we would not want to go without his presentation. And you will soon realize why it is so important to us to be able to listen to his presentation. So we wanted to make sure that he can address us. In the afternoon, when we have the general panel, we will try to establish a connection with him, and there will be the opportunity to ask questions. But please be so kind and inform us about your questions during lunch break so that we can share these questions with him if, technology does not work so well in the afternoon, so that he can answer the questions in advance and we can share the results with you. For more than 10 years, Matthias Englert has been senior researcher at the Öko-Institut EV, the Institute for Applied Ecology. He is responsible for nuclear engineering and plant safety. He studied mechanical engineering and physics at the Technical University of Darmstadt, and there he took his doctorate in physics. And he had a research stay for 2 years at the Stanford University in California, and took him to the Center for International Security and Cooperation. And alongside his technical interest in research, his research also focuses on natural science, in other words, technical peace research, and he also does research on historic, social, and political aspect of using nuclear technologies. So he really covers a broad range of topics with his expertise. And in the latter area, he's a member of the board of the Research Association on Science, Disarmament, and International Security, FONAS, and he's a co-spokesperson of the Working Group on Physics and Disarmament of the German Physical Society. Matthias Englert has in a leading capacity contributed to the latest and most current, and from my point of view, only comprehensive research report on small modular reactors. And this is the research report by BASE. This is the German Federal Agency for Safety and Nuclear Waste Disposal that commissioned that analysis, and the study's analysis is safety analysis and risk assessment of an application of SMR concepts. In this large-scale study, a total of 136 SMR concepts have been researched, concepts that actually led to a dead end in terms of research over the last decades. 31 of these 136 SMR concepts were discussed in a lot of detail. So Matthias Englert is the expert, and he is the man for providing a keynote on the current status of small modular reactor research. And I look forward to his presentation, which will be shown right now.
Yeah.
A very good morning, ladies and gentlemen. Let me greet you from Darmstadt, and I apologize, and I'm sorry that due to various imponderabilities in my life, including the announced railway strikes, I was not able to join you. I would have loved to join you. And I would even say that I would have liked to join you for selfish reasons, because I like being among like-minded people. Normally, I go to conferences where my opinion is an outlier opinion, where I'm a kind of an exotic animal. And with this in mind, I really regret not being able to be with you. But I would like to present my paper and also offer you an opportunity of familiarizing you with the results of our research. I would like to thank the organizers for the invitation and the opportunity to discuss new reactors and small modular reactors. And I will now share my screen. So here we are. So my presentation today is going to be about so-called new reactors, novel reactors, and SMR. And I'm going to talk about safety, proliferation risk, economics, disposal, and feasibility, which is quite a wealth of topics, and I only have 50 minutes. So I have to be quick, and unfortunately I will not be able to cover everything in great details, but here's my agenda. First of all, I'm going to talk about the so-called novel reactor designs or concepts. Then I will briefly talk about small modular reactors, because it's a very similar topic, and then I will discuss what I said and present our conclusions. This is now the status of affairs, the state of play. We did a research study about so-called novel reactor designs or concepts. You can actually read up on it by clicking on the internet address you can see at the bottom of the slide, and I'm going to present selected chapters from it. However, I will not be able to cover 450 pages. First of all, I would like to talk about the terminology, about the so-called novel reactor concepts or alternative reactor designs. In fact, these designs are often very old, so we called the word novel into question. And we also call the idea of generation into question, because very often these reactors are referred to as generation 4 reactors. We will distinguish between the so-called technology lines, which is kind of a headline, and so-called reactor designs or reactor concepts, which are very specific forms of reactors within a technology line. Now, what are these so-called novel reactor concepts? Generation 4 was introduced by the Generation 4 International Forum in at the beginning of the 21st century, and it was thought to be a development towards more economical, safer new reactor types, which actually contribute to disposal or come with lower disposal risk and are also proliferation safe. This forum introduced the so-called technology lines, the sodium-cooled fast reactors, the lead-cooled fast reactors, gas-cooled fast reactors, molten salt reactors, supercritical critical water-cooled reactors, very high temperature reactors, and we also added the accelerator-driven systems. And if we have a look at the idea of the generations, what we can see here is that we can't really call this a generation 4 reactor concept, because looking at light water reactors or pressurized water reactors, the first test reactors were followed by the first power reactors, power plant reactors, then refined power reactors, and then advanced power reactors, such as the AP1000 or the EPR. And we can see the same in BWRs and PHWRs. So actually, we can see that hardly any of them have actually reached generation 2. They actually only made it to generation 1. So that is the initial power reactor. So we decided that we would not call it generation 4, but we said we would talk about alternative reactor concepts. And if we look at these, we can see that there are breakdowns according to criticality, where there are thermal systems, what coolant is used, and we also introduced a couple of specificities. So we could actually find one specific reactor concept for each technology line. We picked one, and you can see that in the right-hand column, and we looked at it in greater detail. Who is actually involved? You can see that here. The various technology lines are being worked on by various countries. The countries working on generation 4 are countries that already use nuclear energy. What are the goals, except for those that I already mentioned? Of course, the optimization of resource utilization, as well as the optimization of disposal, cogeneration using process heat because of the heat produced by these reactors, and of course an improvement of the safety features. And Generation 4 Forum mentions that the time perspective for a commercial fleet to be ready is around 2045. The media have also presented information like 10,000 times less waste, cheap, so that even emerging countries would be able to afford it, proliferation resistant, and readily available in the market. So one can say these so-called new reactors are safe, clean, affordable, reliable, and small, and they will solve the problem of nuclear waste, and we are just on the brink of breakthrough. As for the timeline, actually 3 development phases were discussed, and they are called viability, performance, and demonstration phase here. But there are different types of terms we use. The point is that, first of all, you need to have a proof of principle. You have to make sure that everything works at all. Then there is the performance phase after the viability phase. Thus, performance phase is when you build test reactors and develop and optimize, and then once the system is sufficiently mature, the commercialization phase can start. In 2002, the picture was as follows. It was hoped that no later than in 2015 or 2020, a demonstration reactor would be available, but this didn't happen. I can't really go into detail about all these technology lines, but we'll look at 3 technology lines in greater detail. The sodium-cooled fast breeder, the molten salt reactor, and the very high temperature reactor. And we'll check how far they have come. Let's have a look at the sodium-cooled fast reactor first. This is a layout of the system with a primary sodium circuit, and there is a heat exchanger in the middle that drives a turbine, and the turbine then drives the generator, which generates electricity. And we have similar diagrams for the other reactor types. And we also listed the benefits and drawbacks. Among the benefits are the better utilization of uranium, and the fact that low pressures can be combined with high temperatures. But the drawbacks are problematic reactivity control. There are positive feedback effects. Sodium responds exothermally. It's a chemically reactive coolant, which can lead to sodium fires, which is a problem that they got a grip on in Russia, in Russian reactors, but there is still a problem with the fact that a chemically reactive coolant is not as safe as a chemically inert coolant, which is used in other reactor designs. Moreover, we also have to say that most fast breeders, which includes the sodium-cooled fast breeder, are also discussed in connection with plutonium use, which comes with a proliferation risk. We looked at the BN800 for the study. It's located in Russia, and it's an 820 megawatt electric reactor with sodium as a coolant and MOX as a fuel, fast neutron spectrum. I can't really tell you much more about that reactor due to the lack of time. One could talk a lot about the development and experience in operating it. But here's the timeline for sodium-cooled fast reactors. You can see it at the bottom, and then this is the situation in 2014, and you can compare the timelines. You can see that in 2023, the first demonstration plant should be operating, and the BN800 is actually a first demonstration reactor. It actually was commissioned. However, in other countries, the situation was different. In Russia and China are the only countries that are progressing more or less fast. In France, the Astrid fast breeder development was stopped in 2019. And that takes me to the conclusions. The SFR status is that there are more than 20 prototype reactors. They've been researched on for 70 years, but so far no commercially usable system has come about. The Russian reactor is a first of a kind and has not been turned into a commercially utilizable reactor. SFRs are often designed as fast breeders, and this is considered to be a stepstone into the plutonium industry. In the foreseeable future, this will not be necessary because plutonium is not a scarce commodity. As for safety, there are specific drawbacks and benefits, but the balance, the safety performance balance or output balance is rather bad. The output of reactors is not as good as expected. This could change in the future, so they could become more reliable. Proliferation is a very difficult issue because every fast reactor can produce weapon-grade material, depending on the design. And this takes me to the very high temperature reactors with graphite as a moderator, helium as a coolant gas. There are two designs, one with solid fuels in prism-shaped fuel rods and one as a pebble bed reactor. And you can again see the heat exchanger, and usually this is linked up with a steam system, and gas circuits have also been reflected on to drive the turbine. The gas turbine has not really stood its ground. There were technical problems all the time. The advantages and disadvantages. Advantages would be the high operating temperature of coolant, which could be used as process heat. It also has strongly negative reactivity feedback. Depending on the design, heat could also be used passively, heat from the reactor core, and there is also an embedding of TRISO fuel particles, which has meanwhile become very good, and temperatures can go up to 1600 degrees centigrade. But there are drawbacks. The output has to be restricted to benefit from the passive properties, and incidents cannot be controlled. It does not so much regard the greatest assumed accident, but rather water leakage and the like. The HTR PM in China is a good example. It's a combination of two systems being coupled and driving a turbine, and again the design was done in such a way that the passive safety properties remained. The output temperature targeted is 750 degrees Celsius. There is no containment, and the neutron spectrum is thermal. You can see one of those spherical spherical fuel element, similar to the old type of spherical fuel element built in Germany, but improved using programs, for example, run in South Africa. But the entire principle is based on developments from Germany in the 1970s. The triso fuel can be seen as 3 layers in a graphite sphere. Again, the timeline between 2002 and where we stand today, the VHTR was commissioned, and we can say that it is still in the demonstration phase. The construction in China came with a number of problems, but it was completed rather fast. But now operating experience has to be recorded. We haven't found much about this in literature. However, in principle, one can say that depending on whether you use the HERPM as a performance reactor or demonstration reactor, and I would say it's more of a demonstration reactor, it would be something to build on. A successor model would then be commercially viable. Again, here are a few conclusions. As for the state of play, development has taken 60 years so far. There were ambitious programs which failed. A new attempt was made in China, and we will see where this leads. As for safety, specific advantages are loss of cooling and fuel melting, but in general, it is a difficult concept. Waste has to be considered for various waste properties, and in terms of economic viability, to obtain the passive cooling properties, you have to stick to a lower output. And in China, 2 reactor modules were actually combined in one bigger unit that drives a turbine, and then 2 further modules were added, still driving 1 turbine, or later 2 turbines in one location, to be able to overcome the limitation. And low temperatures are a problem too, because of further secondary process heat that cannot be used. It could be used for hydrogen generation, but it's not enough to minimize the risks. And this was originally thought of and planned in the Chinese program, but they then reduced their expectations to temperatures below 750 degrees centigrade and a water steam secondary circuit. So there is no process heat that could be used. Now for the molten salt reactor, here we have liquid fuel, which runs through the reactor core. This is the novel thing about it. So it can be used in the reactor very flexibly. But a secondary coolant circuit is used for salt melting, and then only in the 3rd stage the heat is then is then discharged and the freeze plug would heat up and the molten salt would be discharged into tanks. The chemical plant for processing the fuel is also very specific, and it can be used for regeneration. There are very many reactor concepts. There are not just molten salt reactors, there are different ways of using fuel. It's chloride salt melting and solid fuels and liquid fuels that can be used. So there is a wide scope of new developments regarding molten salt reactors. In general, the benefits and drawbacks include the benefit of high coolant temperatures, low operating print, and flexible use of fuel. But the development of the salt melting process was quite difficult. There are also corrosive properties, and of course the radioactive material cannot be fully located, which is a problem for the conservative engineers. We looked at the so-called MCFR from the United States, and it's a relatively early model. It's a molten chloride fast reactor in the United States developed by TerraPower. And when we look at the timeline, the demonstration reactor was supposed to be complete by 2020, and we are rather far away from that. It will take at least until 2030 for a demonstration reactor to be completed, and this target might also possibly be missed, but it will depend on the MSR that we are talking about. And this takes me to the conclusions. Regarding MSRs, there were considerable efforts, especially in the 1970s, and then a revival after 2000, but a commercially viable system cannot be expected before 2050. There are certain safety benefits, but these also require considerable technological development, especially in terms of proof of concept and instrumentation, and radiation protection problems have to be considered. As for waste, we have chloride, molten chloride salt, and various flows of waste and relevant nuclides. And again, proliferation is a problem because of the regeneration of fuel. So this was a short insight into what these reactor systems are about, and I gave you a number of examples. And I would now like to briefly talk about the SMRs. We also have an opinion on that, a report on that. And one of the problems is the definition of SMRs. Often it is said it's an advanced system with electric power up to 300 megawatts, designed to be built in factories and shipped to utilities, or can be built in a modular, according to a modular system. So there are different definitions. And what we said was that modularity is not standardized. There is no uniform concept. Many systems are not classic modular systems, and there are also various design cases where, again, it is difficult to delineate SMRs from other types of plants in respect of the fields of application. Mobility properties are often cited. And eventually we came up with a definition that has to do with the output, 300 megawatts, and we looked at various SMR concepts. For example, the land-based systems, the maritime systems, the high-temperature systems, the fast neutron spectrum reactors, the molten salt reactors, and the microreactors. Who developed these? Basically the same countries that are active in the Gen 4 forum, plus a few others. For example, the KLT-40S from Russia, which has been developed since 1998, commissioned in 2020, 35 megawatts, water-cooled and moderated, with partly enriched uranium dioxide dispersion fuel, passive safety systems. It is also designed to withstand aircraft crash, but doesn't have a full pressure containment. And we looked at a few other reactors, such as the KRM-25, which was supposed to be commissioned in 2022, but I read that a new contract for concrete work is now being entered into.
And the new version that is being discussed in the US is the new scale reactor planned for 2026 to be commissioned. Well, in principle, it is based on the light water reactors, and this is the system which must be most credibly be used in the future, must be scalable, 12 modules per plant, and should also be able to be produced on an industrial scale. The plans for the SMR development are actually very broad, based use cases, off-grid, district heating processes, hydrogen, seawater desalination, fighting climate change, and also using it in remote areas. Often it has been said that due to the fact that higher numbers can be produced at industrial scale, electricity can be produced at very favorable prices. Safety and security properties have improved because it only contains minor volume of radioactive modules, and simplification is possible, and these are the proclaimed goals of SMR development. Apart from that, from a technical point of view, the difference is based on size when it comes to advanced or alternative or so-called new reactor systems. And here you can say that for all larger reactors of the technology lines, there is also a so-called small system development. And this brings me to the discussion and then the conclusions. So what do we do with this wide number of reactors, this broad range of reactors? And before I continue, I would like to briefly stop, because otherwise I will be kicked out of my online session and I will have to start again. A few seconds. Okay, so this brings me to the third part of my presentation, discussion of general results and presentation of findings that hold true for the majority of these systems. As already mentioned, a wide range of most diverse options have been presented, and I can only focus on some individual systems, as already said, but there are topics also in terms of conclusions that hold true for the majority of these systems. And this brings me to the economy. And new areas of applications have been suggested. So higher temperature ranges can be used, and process heat can be used. Temperatures higher than 57 degrees up to hydrogen production. But the fact is that high temperatures also are a stress for the material. And when it comes to the concrete implementation of the system, well, the focus needs to be placed on high development, safety and security, and then the broad temperature range application is then left behind, but they want to implement things quickly and instead of focusing on the more challenging development areas. Other areas of applications for the SMR complex, the fact that they can be used in a decentralized manner, and then other renewable energy system with a storage solution could also solve this problem in the same way, and often either due to high development reliability or due to alternative. These concepts then are no longer pursued, and this is in clear contradiction to the line of arguing voiced that modular reactors or new reactor segments could open up new market segments. When it comes to the protection, then you can say that the development and construction period takes at least 25 years in order to make sure that these, so to speak, new systems can be implemented. Generation 4, for instance, according to GIVE, will only be introduced at commercial level in 2045, which is much too late for climate protection, particularly for SMRs. You need to ask yourself how many, what high numbers, thousands of SMRs have to be built to replace the aging existing reactors or to make available the output required, and how realistic is a development scenario involving thousands or 10,000s of such reactors. Not a single SMR concept can lead us to cost reduction expectations, and because according to what is said, that due to standardization this will lead to, and economies of scale, for instance, will lead to cost reductions. The modular structure should also lead to higher productivity levels, but based on our analysis, we can see that it cannot be expected that the disadvantage, in other words, small performance is more expensive than high performance, that these disadvantages can be compensated for by these economies of scale. And so for many years we've seen the same picture, that for the electricity construction costs, this also means that nuclear energy is getting increasingly expensive, considering that solar and wind energy is getting cheaper. So the gap is widening. and it cannot be expected that the cost increase trend to be observed with nuclear energy will not be reversed. As I mentioned, the 800 is a demonstrator concept. Then there are other concepts that are said to penetrate the market, but so far we have not seen such a market penetration. And particularly in the startup scene, we haven't seen any new companies that could achieve any disruptive effects, but mainly private-owned companies used state-funded programs when it comes to funding a demonstration reactors. They always fail because they cost several billions. Even smaller startups use fake it till you make it, make highly unrealistic promises in terms of the timeline, saying that everything will be completed in 10 years. Yes, this is maybe necessary for them to attract private investors, but this is not realistic. And in the nuclear area, there's always this hope of a new Tesla, a new SpaceX, but the technology is a completely different one because there is no leeway for errors. You cannot just have a reactor explode in order to test how it works, in order to learn from your errors. So this doesn't work in the field of nuclear technology because as soon as radioactive radiation comes to play, you cannot do anything at all. So, and then transmutation is another concept that has been most frequently voiced in the context of the so-called new reactor systems. And the idea is that the waste, so critical isotopes and elements are taken out of the waste, and then they are radiated, and then they are no longer dangerous for final storage, so-called transmutation reactors, so-called fast reactors. And they always show this chart according to which it is said if you would eat radioactive waste, then it would be like taking out the transuraniums, these are the lines, and then just a fissile product remained, and then you transmute them, and after a few hundred or thousand years, toxicity is so low that it would not be hazardous at all. But this is most misleading because in the final storage, it is the long-term products that are there. So, and well, this brings me to transmutations, and in these salt molten reactor systems will actually be the best ones. You could actually do transuranium transmutation, but so far only mixed oxide fuels can be used, and all new transuraniums except for plutonium development is still at laboratory scale, and it doesn't generate much benefits because transuraniums are not decisive for final storage because it's the mobile fissile product. So for molten salt reactors, they have very special problems because of the molten salt. And summarizing, you can say, and this holds true for the scenario in Germany, without using nuclear for the nuclear energy, but just to use it to treat waste, this would involve major efforts. At minimum, this would require 100 to 150 years. Well, efficiency is only limited because you required final storage, major burden. So those reduction is low, as mentioned before, and the problems of the usage of nuclear energy will stay. You shift the responsibility safety for waste disposal to future generations, phase out the, well, in Germany means that what we consider, it is a special topic, but, well, I just wanted to highlight that when it comes to safety issues, I could say it is not the system that would solve the safety issue for nuclear power plants. The best system, very less below critical accelerator-driven systems that are, as mentioned, not critical, but serious accidents are possible. In other words, release of radioactivity. So you cannot get rid of the problem, but there are, well, when it comes to safety features, some are better, some are worse. So far, for small modular reactors, they want to achieve today's safety level or even excel, but this proves difficult based on this technology to make a general statement, because in principle you would require a specific system for analysis, and in the context of the studies we use 10 of these reactor systems, but actually it's not so easy because the level of specificity is too low in order to make clear statements. So a wide number of safety features need to be considered. Generally, one could say that passive concepts actually do have their benefits, but I mean other risks are always there. And what we see at that they always want to strike a balance between safety and economical aspects. Lower radioactive inventories are then offset against small containment or other topics. In terms of proliferation, one could say that not water-cooled systems where there is higher uranium enrichment or the use of plutonium fuel as well as reprocessing technology. This is a fundamental detrimental effect on proliferation resistance. So some SMR concepts envisage a long operating timeline, but there's always the issue of proliferation, and then monitoring is always very important. And then, well, how real, how implementable are these things? So reactor concepts have been in development and in use for so many years without seeing a broad-based introduction of the system. The new timelines that have been shown, well, they all start in the year 2000, but actually it started in the 1960s, 1970s, this timeline, and lots of these new introductions have failed times over. Just think of the SMR, just think of the German nuclear high-temperature reactor. These concepts have been known for many years, but they have not been rolled out on a broad base. And if this topic was so successful, then you would expect a favorable mood in society with respect to the usage of such nuclear systems in Germany, as is, for instance, the case in France. Lots of reactors systems have been coming and going. Well, they are still included in lists, although they have not even been built. So the status of development of the individual reactor systems is not transparent. So, and the reasons for failure or why such design changes have been implemented are not so clear. So you really have to look into the detail in order to find out why developers have implemented these changes or changed the design, for instance, modified the design. When it comes to implementing the technology lines of the so-called new reactors, most far progress have been the breeders and the high-temperature reactors. And with the SMRs, you could say that only the water-cooled systems that can use light water can be realized within the immediate future. When it comes to realizing non-water cooled SMR concepts, they always promise fundamental innovations, but there are problems associated with it. The higher operating temperatures, for instance, they say that they are to open up higher efficiency of the fields of application, but this involves more development efforts. Many say that closed fuel cycles can be used, but this is associated with high technological risk. New fuels need to be developed, or reprocessing technologies need to be developed that have not been used at large scale today. Also, some different security and proliferation risks emerge, and then you have to counter these risks by development efforts. Then operating experience is low. Then novel solutions in terms of technological solutions or materials. This means that longer development periods can be expected, and this also goes hand in hand with higher technological risk compared to further development of water-cooled reactors. Or to put it in a different way, water steam sea system is a system people have understood for the last 200 years. So lead or natrium cooled system or molten salt reactors, there we do not have so much experience, operating experience, or not so much experience with the materials or the interactions. This leads me to my general conclusion. So general conclusions we drew in the context of our work. Well, the principles of technology lines, with the exception of accelerator breeder driven systems, have been known since the 1950s, and nevertheless these concepts have not been successfully further developed by the so-called new reactor systems, and we believe the Gen 4 term is faulty because it could be called Generation 2B, but not the Generation 4. So why were these systems developed? So on the one hand, this had to do with innovation policy, but also with geostrategic objectives, and this is what we see also in terms of the Russian reactor program. In terms of the organization models, one can say that from today's point of view, there is no immediate breakthrough foreseeable. Neither industry groups nor the start-up scene succeeded in achieving a breakthrough. The degree of technological maturity is still in the phase of early development for all systems, except, for instance, for the cooled fast reactors, but not a single one has achieved the market penetration goal, and the problem is still to be faced is proliferation and dispersal. And with technology lines and reaction systems, there are some potential benefits, but not a single technology offers benefits across the entire range. Often certain criteria have to be offset against each other. For instance, safety against economical aspects. Potential benefits always depend on the actual implementation in terms of the reactor concept. So in the beginning, the claim in terms of development have been very high, and then slowly they scaled back in terms of the claims, and when it comes to realizing or actually implementing a reactor concept. So the ongoing or planned demonstration reactors do not lend themselves for subsequent broad-based market introduction, still require first-of-a-kind reactor. And what we have seen is that the timelines, and I hope that I have shown it, that the timelines and the milestones have systematically never been met in terms of high-temperature reactors in China and the cooled fast reactors. A demonstration project has been set up, but you must not forget the long development history, so to speak, in terms of fuel and material development. There is a time limits also for high temperature reactors. They actually take a lot of time to be developed. And in terms of SMRs, we do not see any breakthrough for these systems due to massive cost reductions. So this is something we do not see. I hope that I have been able to provide an overview, but there are so many topics that require detailed discussions like transmutation, but actually you should draw a clear line between small modular and large-scale reactors, and each technology line, each reactor concept would lend itself for a lengthy presentation. Well, summarizing, I would like to focus on a quote. The academic reactor and the planned reactor, they are small, unique, they're cheap, they're light, they can be built very quickly, they are flexible, they do not require a lot of development work, and almost everything is there. And the reactor is unfortunately only being studied and has not been implemented yet. The actual reactor is currently being built, is always behind schedule. It requires massive development efforts for some trivial problems like corrosion, for instance. It is quite expensive, and it takes a long time to solve the engineering and development problem. It's large, it's heavy, and it's highly complicated. And this quote is from 1953. Yeah. And this quote is still true. And I would like to share this quote with you by Hyman Rickover. And I thank you for your attention. And I hope to be able to meet you in person soon. I really regret the fact that I cannot be with you today. I wish you an interesting meeting, and I hope that during the panel discussion I will be able to attend, at least remotely. Thank you.